So then we can go to the last power woman, Marcia. And I think she's a pioneer in many aspects, of course, haptics, but also, for example, your work to increase diversity, in example, doctoral training. And Marcia works on several applications like rehabilitation and especially how multisensory touch feedback can improve performances. So send waves of vibrations to Marcia to welcome you. Thank you.
Thank you for the introduction, Bram. These have been really the most personalized that I've ever heard. It's really quite special. Thanks also to Tamim and Stefano for organizing this conference. Thank you for staying through to the end. So as Bram mentioned, I work on a range of different topics, but I thought I would come back to my ICRA roots and talk about a topic that was my first ICRA presentation, and that is this idea of how we are rendering realistic virtual environments using haptic feedback. Before I dive in, the obligatory slide to thank all the people in my lab over the years who've done all the work, and of course the funding agencies who've made it possible. So in my lab, we design robotic devices that can recreate touch experiences for people in virtual environments. I think touch is really one of the most intriguing of our senses because unlike our other senses, it's bidirectional. When you look at this screen, you can imagine the scene, but you can't change what's happening just with vision. You can listen to a symphony, but you can't change what the musicians are playing. But with touch, the experiences that we have are directly coupled to the way that we interact with the environment. And it's this bidirectionality that makes recreating these virtual environments so challenging. Another aspect of touch that's quite interesting from a research perspective is how multifaceted touch is. You can see these hands pushing on the wall and imagine that they're feeling the resistance of the wall in front of them. At the same time, feeling these intricate textures and maybe even the temperature of the objects in their hands. So touch is really instrumental to how we interact with the world around us, but it remains quite challenging to recreate these in virtual environments with the same complexity of the experiences that you see pictured here or that you have every day. So I gave some thought to, what is it that I think makes a touch interaction so compelling? What are the essential ingredients that we need? And I came up with these three. So the first is active touch. We really need to leverage that bidirectionality of our touch sense so that the feedback that we receive needs to be in direct consequence to the actions that we're undertaking. Second, I really think that our haptic interactions need to be multi-sensory, multifaceted, just like our interactions that are pictured on this wall. We need to convey kinesthetic feedback and cutaneous feedback, and I know you heard some of that earlier this week. And third, I really think it's important that as we explore our virtual worlds, that we're unencumbered by our devices that we're designing. So if I think back to my days as a graduate student in the mid to late 90s, when I was preparing my first ICRA talk, how was it that we as engineers were going about recreating these natural haptic interactions? Well, a number of different research groups were developing these haptic interfaces. So this is an image of a phantom, but many devices of the time looked like this. And the goal was to design a robotic device with mechanical characteristics that enabled high-fidelity haptic feedback. Well, what exactly does that mean? Well, we can look at this paper from 1996 that was published in Robotica by Ellis, Ismail, and Lipset for a little bit of insight. So in this paper on the design and evaluation of a high-performance haptic interface, they defined the characteristics that were desirable and optimal for these devices. Things like low apparent mass and inertia, low friction, high structural stiffness, backdrivability, no backlash, et cetera, et cetera. So this is like the dream list for roboticists to try and come up with a device that can meet all of these criteria, many of which are often conflicting demands and difficult to achieve simultaneously. So let's take a little flashback to my own haptic device from the late 90s. So we didn't have a good name for it. We just called it the 3 degree of freedom haptic device, typical engineering name for a device. And if you look at this device, you'll see it exhibiting many of those mechanical design characteristics. The linkages were carbon fiber. It's a parallel mechanism to keep the inertia low. High-performance motors, very low friction, and a really nice, compelling virtual environment experience. Here you can see the individual is interacting with fixed blocks of different geometries in this virtual environment. But if I think back to what I said were the 3 key ingredients of a really compelling haptic interaction, Let's see how we're doing. Well, I said we needed our interactions to be active touch. And this is true. The feedback that this participant is feeling is a direct result of the way he's interacting with the environment. I also said that we need our exploration of the environment to be unencumbered. Well, we are restricting the interactions here to be through a probe, but otherwise, the device is low friction, low inertia, and it's a relatively free space feeling when he's not interacting with the objects that are being rendered. But it's not really multisensory. I'm using spring damper models to create these virtual objects, and so most of the feedback is kinesthetic. It's continuous type forces. So what could we do to address this limitation with these grounded type haptic devices? Well, we could look to some contemporary research that was happening at the time. So these are two papers that came from attendees of this conference. So Allison's PhD work was addressing reality-based models for vibration feedback in virtual environments. And around the same time, Catherine Kuchenbecker was looking at how to improve contact realism through event-based haptic feedback. So let's dive in a little bit into the approach that they were taking. So I'll focus on Allison's paper. So her goal was to improve the realism when contacting rigid virtual objects that she was rendering with her haptic device, so that when she tapped on virtual objects, it would feel like you were tapping on wood or metal or materials of similar rigidity. And so the idea was to take this continuous spring-like model of a virtual surface and overlay it with a decaying sinusoid that would give that transient experience that we get upon contact. If we look at her pipeline of how she implemented this work, she starts by measuring the actual interactions that occur when we tap on objects, and then modeling that with a decaying sinusoid, and then scaling it and implementing it into her haptic device. But there's a piece of this pipeline that really jumped out at me when I was thinking about this talk, and that was this step right here, where she does psychophysical experiments to determine the best parameters for this decaying sinusoid to make that environment experience feel very realistic. So you'll notice a decaying sinusoid represents, in a way, the recorded data from a real object interaction. It's an approximation, it's a model, and yet still we're taking this step to modify those parameters to best suit the user's experience. So it's a really critical step here where we're now taking the role of the human in the loop, their own perceptual performance, their own past experiences that are influencing how they're perceiving that virtual environment. And so while the Robotica paper emphasizes really a focus on the device design and control implementation, here we have a new perspective that is, we have a human in the loop and we really should leverage their experiences. So this was an aspect of my own research as well. So in my PhD research, I was interested in how the haptic display fidelity would influence human perception and performance of basic psychophysical tasks. So we have this unnamed graduate student subject on your left, interacting with the virtual environment. The task is to explore different objects and try to determine if you could detect the object, if you could discriminate the differences in size between two objects, or if you could classify an object as a certain size 1 through 4. And as I had individuals perform these experiments, I artificially degraded the fidelity of the haptic display to see what effect that would have on their performance. And the punchline is, we can accurately identify, discriminate, and detect virtual objects rendered at relatively low fidelity. So I could saturate the force output, I could limit the system bandwidth, I could decrease the surface stiffness, and yet our participants were really quite adept at performing these perceptual tasks with the same level of success that they could when it was a very high fidelity environment. Now, we might prefer the feel of that higher fidelity haptic experience, but we could do the tasks just as well. And there was another, a bit of other work going on around the same time, really starting to dig into, well, what is the effect of the device design and the rendering on human perception and performance in these virtual environments? So again, it's this key here of we can't just focus on the device design and the haptic rendering. We really need to couple this with our human in the loop, with their perception and experience, and take advantage of their skills as we think about how best to recreate these virtual environments. So let's do a little fast forward now and think about what's happening in the field of haptics in this decade, where there's been a real shift to wearables. And I know you heard about that earlier from both Catherine and Allison in their talks earlier this week. We're designing all kinds of wearable haptic devices to fit the arm and to provide feedback all over the body. Let's look at one example that's commercially available. So these are Haptics gloves. And when you look at this, you might think, wow, they're really taking a machine design-centered approach, kind of like those old haptic devices. Now, in this device, we have active touch interactions with the virtual environment. These gloves can provide multisensory feedback, both kinesthetic and cutaneous. But I would argue we're not really enabling unencumbered exploration of the environment. We have these heavy, bulky gloves. So in my lab, we're taking a very different approach to haptic rendering with wearables. We're trying to keep the hands free and provide haptic feedback at the wrist for interactions that are expected at the fingertips. We're taking advantage of the user's perception to map those fingertip experiences that they see visually to a haptic experience at their wrist, meld these together to really have a natural interaction in a virtual world. In collaboration with Meta, we've developed a device called TASB. It's a tactile and squeeze bracelet interface that incorporates 6 linear resonant actuators that can provide vibration feedback for those transient events, just like we saw from the research of Catherine and Allison earlier in the talk, combined with a motor in the sort of the wristwatch area that can provide continuous squeeze feedback in a quite controllable manner. When we use this to render virtual environments, we can then manipulate both the rate of squeeze, the timing of the vibrotactile feedback, and the visual display to create really compelling haptic interactions that feel quite realistic, even when the feedback that you're feeling is at the wrist, and you would expect it to be at the fingertips. So here is my former student, Evan, interacting with 2 virtual buttons that are rendered with 2 different levels of stiffness. What we're really manipulating is the rate of squeeze and the visual display. The way that works is this. When Evan comes in contact with one of those virtual buttons, he feels vibration, that transient effect of contact. As he depresses the button, we're changing the rate of squeeze and the control display ratio, the difference between his finger movements and the rendered finger, to convey a different amount of effort for pushing buttons. More movement maps to a larger stiffness. When we combine those all with accurate timing, the experience that he has is quite a compelling experience about virtual surface stiffness. I'll tell you briefly about a little experiment that we did just to demonstrate this. So in this experiment, we had individuals push 2 different buttons that they saw in virtual environment. One was rendered virtually, and one was a physical button that they could actually touch and interact with. We rendered the virtual button at 4 different levels of virtual stiffness, either with visual feedback or squeeze or a combination of the 2. And then we allowed them to adjust the stiffness of the physical button until it matched their perception of this referred haptic feedback squeeze. This is what it looks like. As they're interacting, you can see they're pushing a physical button and then they're moving their hand in midair, but they're actually interacting with a virtual button on the right. They feel the rendered stiffness of that virtual button and then tune the physical button stiffness to match their perception. When we look at the results for here, I've got 3 plots. We're showing the estimated stiffness, the tuned stiffness of the physical button that they've dialed in to match the perceived stiffness of the virtual button. In red is the tactile only condition, that's just squeeze. Blue is playing only with the visual display, and purple is the combination of the 2. Subjects are feeling an increased stiffness of this midair button as we change the rate of squeeze, as we manipulate that control display ratio with the visual feedback, but it's even more compelling when we combine the 2 in a multisensory framework. So again, we're using this combination of the device design that can provide the cues, our mechanisms for haptic rendering, and leveraging the human-in-loop perception to have that really realistic experience. I promise, Bram, I'm almost done. We're really excited about this as a new paradigm for how we can do intuitive and realistic haptic feedback in virtual environments. We're exploring texture rendering with TASB, where we can manipulate both the vibration and the squeeze for textures of different resolution. And we're also looking at how we can do mass and inertia rendering. So all in all, I think it's really exciting to think about how, considering the human in the loop and our own perceptual capabilities, past experiences, and priors can influence our experiences and really make these haptic interactions quite exciting and believable through active touch, multisensory feedback, unencumbered exploration, and leveraging that human in the loop. Thank you.
Thank you. please raise your hand for questions. Ah, yeah. Heike has a question.
Fascinating work, Marcia.
Thanks, Heike.
So you said larger displacement translates to larger stiffness. Would that also work if you did augmented reality and you could actually see your finger?
So I'll explain the first thing first. So yes, when you are pushing one of these virtual buttons, the more you have to move your arm, you perceive that as greater effort, and so the spring is perceived as stiffer. Opposite than a real spring, right? And when you couple that with a visual distortion, then that sort of amplifies the experience. If we were in augmented reality where you can also see your finger, we lose the visual manipulation on top of that. And so I do think that we would have to explore this a little bit. But yes, this combination of what the effort that active touch exploration is like, and then the rate of squeeze feedback is really creating this haptic experience.
Okay. Another question?